Hi, I'm Brian Cox. I'm a Professor of Particle Physics at the University of Manchester and the Royal Society Professor for Public Engagement in Science. And amongst other things, I'm the author of several science books, including Black Holes, the key to understanding the universe.
What if everything we thought we knew about space and time was just the surface? Imagine a region in the universe so strange, so powerful that it traps even light, where time freezes, space bends, and reality breaks down. These are black holes, cosmic monsters once thought too bizarre to exist, now at the center of some of the biggest breakthroughs in physics. But here's the twist. They might not just be massive objects, they could be the keys to understanding everything. Time, gravity, even the origin of the universe. In this video, Professor Brian Cox takes us on a thrilling journey, from classical physics to the quantum edge, where science fiction begins to sound like science fact. Buckle up, because this isn't just a deep dive into black holes. It's a voyage to the deepest truths about our universe. Black holes, from fiction to foundation. Black holes weren't always the stars of theoretical physics. For decades, scientists thought they were mathematical oddities, never to be found in nature. Even legendary physicists like Steven Weinberg once hoped they didn't exist, simply because they were so puzzling. But today we know, black holes are real, and they don't just warp space, they challenge our very understanding of reality. The idea of a black hole goes back as far as the late 1700s, when thinkers like Jean Michel and Pierre-Simon Laplace speculated about dark stars so massive, not even light could escape. They were using Newtonian physics back then, long before Einstein introduced his general theory of relativity. But even in Newton's time, the notion of an escape velocity faster than light was captivating. Einstein's theory, published in 1915, changed everything. It described gravity not as a force, but as the warping of space and time. Soon after, a physicist named Carl Schwarzschild discovered a solution to Einstein's equations that described a region of space where this warping became infinite, what we now call a black hole. Still, many physicists resisted the idea. After all, how could nature create something so extreme? That resistance began to fade in the 1960s when Roger Penrose and Stephen Hawking showed that under the right conditions, like when a massive star collapses, black holes must form. And with the advent of X-ray telescopes and radio imaging, we've actually seen the shadow of these beasts in space. They're no longer theory, they're fact. But what makes black holes truly fascinating isn't just that they exist. It's what they tell us about the universe. They force us to look at the limits of Einstein's theory and ask, what lies beyond? Where time stops and theories collide from the outside, a black hole looks like a sphere of darkness. But what really defines it is the event horizon, the invisible boundary where escape becomes impossible. Cross it, and not even light can return. But here's where things get weird. To an outside observer, time appears to stop at the event horizon. This isn't science fiction. It's a direct prediction of Einstein's theory of general relativity. If you were watching an astronaut fall toward a black hole, you'd see them slow down, freeze, and never quite cross the horizon. From their perspective, though, everything seems normal. They fall right through. Time ticks at 1 second per second on their watch. It's a bizarre consequence of how gravity warps both time and space. These paradoxes troubled scientists for decades. Was the collapsing star just stuck forever at the event horizon? Was time really stopping? Eventually, physicists realized that this contradiction wasn't a bug in relativity, it was a feature. The confusion stemmed from thinking of time and space as fixed. But in Einstein's world, they're flexible, and they behave differently depending on where you stand. Yet relativity isn't the full story. Black holes don't just mess with space and time, they challenge quantum mechanics too. Inside them lies a region called the singularity, where gravity becomes infinite and physics breaks down. According to general relativity, this isn't even a place in space. It's a moment in time, the end of time itself. But physics hates infinities. They're a sign that something's missing. To understand what's really happening at the heart of a black hole, we need more than Einstein. We need a new theory, a quantum theory of gravity that merges relativity and quantum mechanics. And this is where the story gets even more interesting. Hawking's fire. when black holes begin to glow. In the mid-1970s, Stephen Hawking changed everything. Until then, black holes were seen as eternal prisons, objects that swallowed everything and gave nothing back. But Hawking's groundbreaking calculations showed that black holes aren't completely black. In fact, they glow. Using the principles of quantum mechanics, Hawking demonstrated that black holes emit particles in a process now known as Hawking radiation. Here's the wild idea: space is never truly empty.
Even in a vacuum, quantum particles constantly pop in and out of existence. Near a black hole's event horizon, one particle can escape while the other falls in. The escaping particle becomes real, carrying energy away from the black hole. The result? Over time, the black hole loses mass. It shrinks, and if you wait long enough, trillions of years for the big ones, it completely evaporates. But this discovery raised a terrifying question. What happens to the information about everything that fell in? According to classical physics, information is never truly lost. You might burn a book, but in theory, you could reconstruct it from the ashes, smoke, and light. But Hawking's calculations suggested otherwise, that black holes were information erasers, violating a fundamental law of physics. This became the infamous black hole information paradox, and it shook the foundations of theoretical physics. If Hawking was right, it meant we needed to rethink everything, and if he was wrong, we still had to explain how information escapes a region where nothing else can. For decades, physicists argued over this. Some, like Leonard Susskind, believed information must be preserved. Others, including Hawking himself at first, weren't so sure. But the deeper they dug, the more black holes seemed to hold the secrets, not just to gravity, but to the very structure of reality. The paradox that changed physics forever. The black hole information paradox didn't just trouble a few scientists, it became a full-blown crisis in theoretical physics. If information really could be destroyed, then one of the core principles of quantum mechanics, unitarity, the idea that information is always preserved, would be shattered. That would mean quantum mechanics, the most successful theory in science, was incomplete or wrong. But if the information was preserved, how could it escape a black hole? This wasn't just an abstract thought experiment. It forced physicists to re-express and challenge the deepest assumptions in both general relativity and quantum mechanics. In the 1980s and 90s, thinkers like Leonard Susskind and Gerard 't Hooft argued fiercely against Hawking's original claim. They insisted that if black holes really destroyed information, it would break everything we knew about the universe. But the math didn't lie. According to standard calculations, once the black hole evaporates completely, all that's left is a mist of Hawking radiation. Thermal, featureless, and seemingly devoid of any memory of what fell in. That defies everything quantum theory teaches us. The solution? Physicists began to look deeper, not just at what goes in or comes out of a black hole, but at the structure of space and time itself. Could it be that the event horizon, what seemed like a surface of no return, actually encoded information in some mysterious way? Could space itself store data like a cosmic hard drive? These ideas began to spark a revolution. Suddenly, black holes weren't just astrophysical oddities. They were laboratories for quantum gravity, offering clues about how space-time might behave at its most extreme. The paradox cracked open a window into the very fabric of reality, forcing science to explore questions once considered unanswerable. Holograms, boundaries, and emergent reality. If you thought the idea of glowing black holes was wild, get ready for this. What if our entire universe is a hologram? This bizarre notion gained traction thanks to the work of physicists exploring the black hole information paradox. A key insight came from Jacob Bekenstein, who in the 1970s calculated that the amount of information a black hole can store is proportional, not to its volume, but to its surface area. In other words, the black hole's event horizon encodes everything that ever fell into it. This was the seed of a much bigger idea, the holographic principle. Developed further by Juan Maldatina and others, it suggests that everything we experience inside a region of space, including time itself, might actually be encoded on its boundary, like a 3D movie projected from a 2D screen. It's not just a metaphor. In very specific mathematical models, this principle holds perfectly. There's a complete equivalence between a theory that lives on the boundary of a space and one that describes the space's interior. They're not approximations, they're exact mirrors of each other. This has massive implications. It hints that space and time aren't fundamental. They might emerge from something deeper, something quantum and entangled. It's like discovering that the world isn't built out of atoms, but out of relationships between bits of information. Even more surprising, the way black holes store and protect information bears a striking resemblance to how quantum computers store data. In both cases, information isn't held in just one place. It's spread out redundantly so that even if parts are lost, the whole can be recovered. What black holes reveal about the beginning of everything? So, what does all this tell us about the origin of the universe? Black holes and the Big Bang may seem like opposite concepts. One marks the end of time inside an object, the other marks the beginning of time everywhere. But surprisingly, they may be two sides of the same coin. Inside a black hole, at the very center, lies a singularity, a point where gravity becomes infinite, time ends, and space collapses. In Einstein's general relativity, it's the place where all the equations break down. That same kind of breakdown happens when we rewind the universe back to the Big Bang. So, if we want to understand the start of everything, we first need to understand what's happening inside a black hole. Here's the good news. We can't observe the Big Bang directly, but we can observe black holes. We can watch them collide, measure their radiation, and test our theories. Black holes are like natural laboratories that give us access to physics under extreme conditions, conditions that mirror those of the early universe. The greatest question: are we alone? After exploring the deepest corners of space, black holes, and quantum gravity, you might think we've reached the limits of cosmic mystery. But there's one more question that haunts both scientists and dreamers alike. Are we alone in the universe? Professor Brian Cox transitions from physics to philosophy with a sharp question first posed by Enrico Fermi. Where is everybody? With hundreds of billions of stars in our galaxy alone, most of them with planets, and a 10 billion year head start, why haven't we heard a whisper from intelligent life? This is the Fermi paradox, and it's not science fiction. It's a scientific crisis. The numbers say we should have encountered someone. The silence says we haven't. One possible answer? Maybe complex life is incredibly rare. Yes, microbes may be everywhere, on Mars, on moons like Europa, or Enceladus. But the leap from single-celled organisms to civilizations capable of building telescopes and spaceships might require a near miracle of biological stability. Earth has had 4 billion years of unbroken biological evolution. That's a cosmic luxury. Our sun stayed stable, supernovae didn't fry the planet, and asteroid impacts never fully reset the clock. Maybe that kind of luck almost never happens. Or maybe civilizations don't last long. Once a species develops technology powerful enough to reach for the stars, it may also gain the power to destroy itself through nuclear war, climate collapse, or unregulated AI. This is the Great Filter Theory, that civilizations either fail to arise or they wipe themselves out. Another idea? Maybe the galaxy is full of civilizations, but they're choosing to stay silent. They figured out that announcing your presence in a potentially hostile universe might be the worst possible move. The so-called dark forest hypothesis suggests advanced life stays quiet, hidden, and unreachable by design. Brian Cox offers a chilling thought. Maybe we are the first and only intelligent civilization in the Milky Way. If that's true, Earth is not just a planet. It's the only island of meaning in a galaxy of 400 billion stars. And that gives us a tremendous responsibility to preserve it, protect it, and not waste the one shot at intelligence the galaxy may ever know. So if you've ever stared into the night sky and wondered what's out there, know this: the universe is whispering, and black holes are where it starts to shout.